Hey there, welcome back for all of you that have watched previous videos for this exam. And hey, welcome for the first time if you're a newbie here. But we are going to continue the 2012 Practice AP Calculus AB exam that College Board put out a decade ago. All right, we are going to do the last, 7 problems of Section 1, Part B. There are 4 other videos that cover the other multiple choice problems. Section 1, Part A, and the first part of Section 1, Part B. Okay, sweet. We get to use a graphing calculator. And since we're on that topic, I have recently begun to get a lot of inquiries about what type of calculator should I get. All right, the set that I have for my classroom, the set that I own, the school doesn't own it, that I own, are the TI-84 Plus CE edition. Why do I use the CE editions? It's the same digital one that I have on this board here, because when I graph things, they have different colors. It just looks a little bit cleaner, the display. I really highly advise you get that if you can. And it comes in a lot of sweet colors. I personally love the color green. My personal TI-84 Plus CE is the mint green. I love it. But in the description, I have put links to all the cool colors that the kids seem to like. There's purples, blues, reds, greens, there's blacks, grays, whites, there's gold, silver, rose gold. And then I also put a link to a case there that I use as well. It's, you got to protect that. They're kind of pricey. They're about 130, anywhere from 100 to 150 bucks in that price range. But I highly advise getting them. So here we go. Here's the lame personal pitch. Follow me, because that helps you by you getting notifications when I put up new videos, like the free response questions for this exam. Like the video, because that helps me. And while you're down there ringing that bell in the comments, if you want to see a certain year test for Calc AB, let me know, because I do take requests. All right, let's get started and finish the multiple choice for this exam right now. Oh man, I love me some graphs and tables and charts. Woo! Almost as much as I love the calligraphy pen on this smartboard. But 85 says, the graph of f prime, the derivative of f, is shown in the figure above. The function f has a local maximum at x equals which one of these values? First thing I'm going to do, this is the graph of f prime. So my y value is the value of f prime, which is the slope of f, okay? And keep in mind, any y value that's above the x-axis is considered positive. Therefore, I should have a positive first derivative or positive slope anytime I'm above the x-axis. Y values below the x-axis have a negative y value. So therefore, they have a negative first derivative or a negative slope. This is helpful. Why? Because we need to find where the local maximum is. Maximums occur when I go from a positive slope or first derivative to a negative slope or first derivative, okay? Which in the case of our graph, it's a positive y value to a negative y value, okay? And we should have a critical point in between, which is where y equals 0. So let's take a look at all the values where y is equal to 0, and then we'll see if it changes from positive to negative at that point. Meaning, right here, that's a y equals 0, so that's a critical point. And right here, it's a critical point. Okay, it's where y equals 0. All right, it's where my first derivative is equal to 0. That's the definition of a critical point. Okay, and that's where we can possibly have mins and maxes. All right, so let's look. As we go left to right on our graph, I start with the negative y values, and then I go to positive. Okay, so if I'm looking at the original graph, that means I have a negative slope to my positive slope. Okay, so at this critical point, I actually have a minimum. Okay. So let's go to our second critical point, the one located at x equals 1. Okay, as I go left to right in the graph, I go from a positive slope to a negative slope. These are all negatives. Okay, so that means at this critical point right here at 1, Okay, on the left side of it, I have a positive slope. And then to the right of it, I have a negative slope. So that is definitely a max at x equals 1. Right there. That's where my maximum occurs, at x equals 1. Pretty good. I like it. Me gusta. Problem 86. Oh, it's my lucky day. Tables. I mean, guys, I can't stress how much I love tables and charts and graphs. Oh, my. Oh, my. So 86 reads, if f prime of x is greater than 0 for all real numbers of x, and the integration of f of t dt from 4 to 7 is 0, which of the following could be a table of values for the function of f? All right, well, let's see if we can just, get rid of some of these based on the two pieces of information that they gave us. Let's start crossing out some answers we know definitely cannot work. And let's start with the first derivative has to be greater than 0, not equal to 0, not greater than or equal. It always means the first derivative must be positive. That means I must always, always, always have an increasing function. Always. So A, -4 to -3 is increasing. 3 to 0. Okay, that's increasing. It's good. B, all right. B goes from -4 to -2. That's increasing. -2 to 5. That's increasing. Okay. C, -4 to 6. That's increasing. But 6 to 3 is decreasing. It cannot be C. Remember, for all values of x, there shouldn't even be a point where it decreases. D, this is not an increase or decrease. That's a 0. Remember, my first derivative, or my function of f, must always increase. Not be equal to 0, but always increase. So it cannot be D. All right, and this goes from 0 to 4. That's an increase, and 4 to 6. Okay, so we got rid of two choices, C and D. So we have A, B, and E left. And this is where we're going to look at here, this right here. Integration is the same thing as area under the curve. Okay, and that's the way we're going to look at it. The area under the curve needs to be 0. And you might think to yourself, well, area is never 0. Yes, you are correct. However, when we do area under the curve, unless we got the absolute value signs there, okay, whenever we're talking displacement, not total distance, that's, I guess, a conversation for a future problem maybe. But area under the curve, anything that's above the x-axis is positive, and anything that's below the x-axis is negative. So if I kind of have the same, if I have some positive values and some negative values, they'll cancel. So I want part of my graph, I want something that's, okay, I'm going to have a graph, maybe a little bit's below, a little bit's above. So this will be considered negative, this will be considered positive, and they'll cancel out to be 0. I don't want anything that's all positive, because then it'll be positive, it won't be 0. Likewise, I don't want anything that's all considered negative. Okay, so let's take a look at these. And I want a function that goes both below and above the x-axis. Let's look at choice E. Okay, this is constantly above the x-axis. If I had to plot those points at 4, 5, and 7, 4 is 0. 5 is at 4, and 7 is at 6. This is constantly above. I know I used red. That's positive. That would never be 0, the area under the curve. The only, okay, A is constantly below. Okay, I'll do that in blue. Okay, at 4, I'm at -4 down here. At 5, I'm at -3, and at 7, I'm at 0. So that's constantly below. That's negative. It can't be this one. It has to be B. How come? And I'll do this in orange. In fact, I'll do a new set here. Here's 4, 5, and 7. Okay, do this in black. 4 is at -4, 5 is at -2, and 7 is at 5. So this graph kind of comes like this. All right, so we have this area that's negative and this area that's positive. That's the only one that gives us a chance to negate each other out, to cancel each other out so that my area is 0. This is the only one that could be the table to represent our scenario above. There's a lot of talking in that problem. Guys, I must be living life right, because this is our third problem. This is the third problem that involves a graph or tables or charts. Oh my. 87 reads, the graph of f double prime, the second derivative of f, is shown, not above but below, from -2 to 4. Okay, so the first thing I'm going to do, you know what I'm going to do. My y, that represents the second derivative. Okay, from -2 to 4. All right. What are all intervals on which the graph of the function f is concave down? In order for f to be concave down, the second derivative must be negative. Okay? And if this is the graph of the second derivative, that means y must be negative. All right, well, I think there's only 2 places where I have negative y values. From here to here. So from -2 to, I don't know, maybe -1. That's one of the intervals. It's positive up here, but then it's negative again here from 1 to 3. That's not a coordinate, that is an interval. So from -2 to -1, and from 1 to 3. That's the only place right there. Man, that was a cakewalk. Woo! And speaking of walks, a person whose height is 6 feet is walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate at which the person's shadow is lengthening? Okay. Okay. All right, so the dude here, or the girl, or the person, is 6 feet tall. The street lamp is 15 feet tall. Okay, they are walking away, meaning from here to here. This rate is a +4. Okay, and they want us to figure out the length of the shadow. I guess we'll call that, I mean, I hate to use S because it looks like a 5. We'll call that X. We're trying to figure out this part from here to here. Okay, and from here to here is my 4. I mean, I don't like this because to me, it doesn't really even use calculus. It uses geometry, which isn't even pre-calculus, which isn't even algebra 2. It's before that. You're years removed from this. If I create triangle, we have 2 like triangles. We have, oh, I got to use the big one here. Boom. This big triangle is similar, okay, and now we'll use this mint green because, you know, that's my calculator color. They're similar, okay, they're similar triangles, all right, and sides of similar triangles have like the same ratio, okay, and what do I mean? That means this side of the orange triangle, that means I should circle that in orange. 15 is to, this whole side is 4 plus x, okay? So 15 is to 4 plus x. That's the same thing as, and now I can use my mint green again, 6 is to just x. Okay, now keep in mind, if this is the upright side, and I'm going to put that in the numerator here, then this upright has to be in the numerator here, okay? This base is in the denominator, so this base needs to be in the denominator. So let's just cross multiply and solve, and it's really that easy. 15x equals, I'll distribute the 6, 24 plus 6x, subtract 6x from both sides. 9x equals 24, divide by 9. I mean, we can use a calculator here, but 3 goes into both of those, 8 over 3. And 3 goes in there twice with a remainder of 2/3, which is 2.6666. Boom. I mean, you see why I don't like that problem? I don't even know if you guys would remember doing that. I mean, normally we do this. We got ds. We're coming up with equations. We're trying to bring in, change in y over change in x, or excuse me, we're trying to bring in dy over dx, and then we're trying to bring in the derivative for the shadow, and we're coming up with it. It really is just similar triangles. This question has no real purpose or reason or rhyme for even being in an AP Calc AB test. That's just my opinion. I'm sure someone could find another reason to have it here. 89. Oh, no charts, no graphs. I mean, we had four. Probably that graphic of the guy walking away. That was kind of cool. But here we go, and we're definitely going to use the calculator here. So I can tell that by the choices A through E. Now's the time where you need a calculator. 89 reads, a particle moves along a line so that its acceleration for time t is greater than or equal to 0 is given by a of t, which is t plus 3 over the square root of t cubed plus 1. All right? If the particle's velocity at time equals 0 is 5, what is the velocity of the particle at time equals 3? Okay. This is actually a lot easier than you think it is. All right, fundamental theorem of integrals. All right, it's just, here we go. Anytime I integrate something with bounds, in most textbooks they use small f of x. That's just the original equation with the upper bounds minus the original equation with the lower bounds. Okay. This is basically what we're going to use. And we have calculators that do it. So it's awesome. So I'm going to integrate acceleration. How come? Because we have position, we have velocity, and we have acceleration. These are all one derivative away, which means I go backward for integration. Okay? We have acceleration. We want velocity, so we're going to integrate. I'm going to integrate my acceleration, which is this right here, okay? And I'm going to do that from time 0 to time 3. That should be, remember, the original equation, going back one, would give me velocity. I should put velocity at 3 minus velocity at 0. These should be equal based on what we have right here. Absolutely, okay? So what are they asking us to find? The velocity at 3. I need to find v of 3, which means I should be able to put this in a calculator, but I should also have, if I'm finding this, I should also have v of 0, which I do. The velocity at time 0 is 5. Okay? So really what I'm going to do is I'm just going to add 5 to both sides. So I'm going to say 5 plus the integration from 0 to 3. I'll put in the actual formula we need. It's t plus 3 over the square root. It's t cubed. Is it plus 1? Plus 1. dt. And that should equal v of 3. All I did was move this over to this side. All right? I can literally put this in the calculator and hit enter, which is what I'm going to do. Oh-do-do, now's the time to be looking to buy one of those calculators. Well, you probably already have one. But if you don't, get the mint green one. It's sweet. That's the one I have. So we're going to go math 9. That's integration from 0 to 3 of my fraction. Okay? X plus 3 over the square root of x cubed, pop off that exponent, plus 1 dx. And oh, by the way, I still need to add 5. So I can hit enter here, then add 5, or I can just put plus 5 here. 11.710. Yeah, there you go. This is my answer. And all of our answers are 3 decimal places. So it's just going to be 11.710, which is choice E. Number 90. They try and get a little sneaky here, but we know better. We know better. Let f be a function such that the integration from 6 to 12 of f of 2x dx equals 10. Which of the following must be true? All right, well, when I look at my choices here, A through E, it looks like the 2x is gone, and they put a t there. We normally do U substitution. So instead of a t, I'm going to use a u. If you want to use a t, you can. But again, we do U substitution, so I'm going to use a u. I need this. Well, man, that green, I'm loving it. Let's go with this light. Oh, that's pretty. Okay, I'm going to need f of u. I need that 2x to go bye-bye. I'm going to need du, whatever. So I'm going to say, let's make u 2x, which means du is going to equal 2 dx. But I don't have a 2 to sub out here anymore because it's already gone bye-bye. So I'm going to multiply both sides by a half. So now in for my dx, I'm going to put 1/2 du. Here's the du. I put the 1/2 on the outside of the integral. Any constant I always put on the outside. I still need to change my bounds. Don't leave your bounds 6 and 12. Because right now, these are x equals 12, x equals 6. I need x equals 6, x equals 12. I need u equals my upper bound and u for my lower bound. So my upper bound had x being 12, which means if I put a 12 here, that means that's 2 times 12. My new upper bound in terms of u is 24. Okay? My lower bound was 6, x equals 6. Let's put a 6 in for this x. It's 2 times 6. My new lower bound should be 12. So here's the problem, okay? I have 1/2 integration from 12 to 24 of f of u. I mean, you could say t, but I like f of u. Sorry, childish. Du equals 10. If you want, at this point, you could make these t's, all right? But I just, we do use, all right? I don't see that anywhere. In fact, I don't see it equal to 10 at all. But what you should notice, my friends, y'all my friends, none of these integrals have a constant in front of them. So I need to get rid of this 1/2 by multiplying it by 2. Now this is bye-bye. What I do to one side of the equal sign, I need to do to the other. So now I have my integration from 24 to 12 of fu du equals 20. And this is definitely there. Okay? That is definitely choice B. Look at choice D. Everything's good except they kept the bounds in terms of x. Do not fall for that. Remember, every time you use U sub, every time, you also need to change your bounds. It's like Christmas in November. Oh, 91 has a table. Let f be a polynomial function with the values of f prime of x at selected values of x given in the table above. That didn't sound right, but I read it exactly. Weird. Which of the following must be true for values of x between -2 and 6? Okay. The graph of f is concave up. The graph of f has at least 2 points of inflection. The graph, it says f is increasing. F has no critical points. F has at least 2 relative extrema. Now, obviously, it's talking about the second. Okay, let's write this down here. Let's write this down before we start talking filth and flarn and filth here, guys. Concave up means the second derivative is positive. The graph has at least 2 points of inflection. That means the second derivative, there are 2 times where it might equal 0. Okay? 2 at 2 points. Okay? F is increasing. That means the first derivative is always positive. F has no critical points. That means the first derivative is never 0 or undefined, I guess I should say. And f has at least two relative extrema. Okay, that would have to have, you would have to have two critical points, which means the first derivative would have to equal 0 at least twice. And then you'd have to go from positive to negative or negative to positive first derivative. That's how you get mins and maxes. All right, let's take a look at this junk here. The graph of f is concave up. All right, so in order to evaluate this, if I have the first derivative, the second derivative is the slope of the first derivative, okay? That means the whole graph of f is concave up. That means the slope of this first derivative is constantly positive. Okay, that's decreasing right there. That's increasing, that's decreasing. That's increasing, but that's decreasing as well. It is not always positive. Okay, so we can't do that. All right, good. B, the graph of f has at least 2 points of inflection where the second derivative is equal to 0. And it's, okay, so this would mean the slope or the first derivative. Yeah, the slope of the first derivative. The first derivative slope would have to change 2 times. Okay, we just said this is a negative slope. This from here to here and here to here is a positive slope. Then it goes back to a negative slope. So it changes here from negative to positive. And then it also changes here somewhere from positive to negative. That is true. Boom. There's your answer. F isn't always increasing. We already figured that out. F has no critical points. I mean, you know, that could be true, but it's not a must. And F has at least 2 relative extrema. You know, no. Here you go. Choice B, based on the table they gave us, that's your answer. All right, here we go. Number 92, and we're done, thank God. Let R be the region in the first quadrant bounded below by the graph of y equals x squared and above by the graph of y equals a square root of x. R is the base of the solid whose cross sections are perpendicular to the x-axis are squares. What's the volume of the solid? Well, first of all, I hope you know that anytime I want to find the volume of a solid, okay, I need to integrate the area of said solid. In this case, it's a square. That is side squared. That's the area. So I want to take the integration of my side squared ds. Okay, because that's the area of our squares. Okay, let's get a visual here. Okay, I'm going to need some bounds. Okay, I'm obviously going to use a calculator. Look at my 5 answers. They're all decimals. Okay, let's graph y equals x squared and y equals a square root of x with our lovely calculator that you're going to click on the link below and purchase because it got all a bunch of sweet colors there. Mint green, by the way. It's hot. That's the one I own. So let's turn this on and let's graph, okay, x squared and the square root of x. And if I graph these things, I notice they're going to intersect at 2 points. And it's very, very tough to see them at 0 and 1. So I'm going to zoom in. I'm going to use my zoom box. I love zooming in with the box. It's so awesome. Okay, so I'm going to go over here, hit enter, go up a little bit. Yeah, right there. Move over a little bit. Ooh, bam. And there we go. This is x squared. And red is the square root of x. In fact, what I should do is I'll bring this out here. And yeah, we got that little spider dude hanging out in the middle there. All right, so my bounds are going to be from 0 to 1. So I got 0 to 1. In fact, we can start a new integration here from 0 to 1. Okay, red is a square root of x, and blue is x squared. This is the point you need to understand. I need to square the side. What is the length of the side? The side is the difference from here to here. This is the square I'm making. It's just slanted. And these are all the squares. They get smaller and smaller and smaller. So the side is literally this part, I got to pick a bright color, pink. The side is the distance between your two functions, with the square root of x being on the top. Wow, that's really terrible. I don't know why I decided to put light gray on light gray, but let's go green here. Square root of x is the top one, and x squared is the bottom. So the difference here, the difference is subtraction. So my side is going to be the square root of x minus x squared. That length, okay, that length that I just made right here, that's the side. But remember, it's side squared, which means I have to square this. Once you come up with this equation, you just put it in a calculator. I mean, guys. Let's go math 9. From 0 to 1. Parenthesis, the square root of x, pop out of the square root, minus x squared. I need a closing parenthesis. I have 2 open parentheses, so I need 2 closing parentheses. But let's not forget, that's our side. We still need to square the side. Okay, look what I have written down below here with a green and purple. I need to square that, and I did. X, 0.128, every day, all day long. Okay, I'm going to round this to 9 because the number after it is 5 or bigger. 0.129. Oh my God, so easy. You know, I wish I had you in my calculus class. I do. I wish I had you in my calculus class, because you'd be the type of kid who'd come up here at lunch and bother me. But you know what? I'd enjoy you being up here. We'd watch fail videos of people falling off skateboards and falling on ice, and we'd laugh and laugh. And then you'd cry when we had a calc test. But you know what? You'd get through it. You'd get through it. We're done. Don't forget, follow me on YouTube, because that's the only way you get notified when I put up videos, especially when we start doing the free response question, because it's 1 video per question. And then like the video, because that helps me. And in the comments, if you want to throw down a test you want to see, hey, I take requests. I'll see you later.